In this problem we have f of x is natural log of 1 plus x to the third power. And we're given the Maclaurin series for natural log of 1 plus x, which is x minus x squared over 2 plus x cubed over 3, etc. And we want to use that series to write the first four non-zero terms and the general term of the Maclaurin series for f. So one thing you might recall is that this natural log of x, it comes from the family of 1 over 1 minus x. So 1 over 1 minus x is where this all begins, and that is 1 plus x squared plus x to the third, etc., which is x to the n. You can either memorize that or you can do the long division method, dividing 1 by 1 minus x, and you'd get 1 and 1 minus x. 0 minus negative x gives you positive x, and so you can see from there it will continue in that way. The second one that's important is the 1 over 1 plus x, which is really 1 over 1 minus negative x. So it's really the same as the one above, only we're going to substitute negative x for x. The even power terms will stay positive and the odd power terms will become negative. So that will become 1 minus x plus x squared minus x to the third, etc. And that's the one that well, no, it's not the one that we have here. The one that we have here in this problem is one step further from this. This would be negative 1 to the n, x to the n. Now you recall we can also from this take the integral of 1 over 1 plus x dx, and would really be, we'll just leave it as such for right now, and that is just the term by term integration. That would be x minus x squared over 2 plus x to the third over 3 minus x to the fourth over 4, etc. 0, 1, 2. Well, this is the one you might recall that starts off at 1, and probably for convenience sake, since if we started at 1, this would just be negative 1. We'll come back to that exponent in a second, and we have x to the n over n. Now, in order for the first term to be positive, since we're starting at 1, we can't start at n, we'd have to start at n plus 1. And that, since this is the integral of 1 over 1 plus x, we know that to be the natural log of quantity 1 plus x. So that's where we get to this. You can either memorize that, or in this case they give it to you, fortunately for that. I'll just erase some of that stuff, and if necessary we'll come back and erase the other stuff too. Now what we want then is, using that, we want to find the natural log of 1 plus x to the third power. And so that is simply going to be f of x. We're simply going to replace x with x cubed. And so we get x to the third minus x to the sixth over 2 plus x to the ninth over 3 minus x to the 12th over 4. So we want the first four non-zero terms and the general term. Alright, since, remember with these, that we started with 1 with the natural log, so with this we will also start with 1, and it'll simply be 1, 2, 3, 4, n in the denominator, and negative 1, we'll worry about the exponent in a second, and x to the 3n. Now negative 1 needs to start off positive, so once again we'll leave that as n plus 1, so that's positive. Alright, so that's the first part. That is A. Now, the next thing we want to do is to find, or the radius of convergence of that Maclaurin series is 1. We want to determine the interval of convergence and to show the work that leads to our answer. So for an interval of convergence, we need to use the ratio test. That is limit as n approaches infinity of the n plus first term. Actually, we don't need the negative 1 there, so it's x. It's not x to the 3n plus 1. You have to remember it's x to the 3 times n plus 1, or x to the 3n plus 3. Absolute value over n plus 1 times the reciprocal of the n term, and that would be n over absolute value of x to the 3n. We simplify this a little. We get the limit as n approaches infinity of n over n plus 1. We know that to be 1. And then we have absolute value of x to the 3n plus 3 over x to the 3n. And that all leaves us with absolute value of x to the third power. In order for the series to converge, that must be less than 1, and so once again we know that x has to be greater than negative 1, less than positive 1. Now we still need to test the endpoints. So at x equals negative 1, we're going to plug into our f of x function x equals negative 1, and we will start off with then negative 1, and so that will be negative 1 to the third minus, I'll plug in the negative 1s and then we'll simplify it. We'll do this for a few terms. And let's see what we get. We have negative 1, then minus 1/2, then minus 1/3, and so this is just the negative of the harmonic series. So this is really just negative 1 over n, and since the harmonic series diverges, this also diverges. Alright, let's test at x equals 1. At x equals 1, we get 1 to the third minus 1 to the 6th over 2 plus 1 to the 9th over 3 minus 1 to the 12th over 4, and you may see that this is becoming the convergent alternating series. Alternating harmonic series, I should say. So this is negative 1 to the n over n, which converges. It converges. It's in reality a p-series with, no, it's an alternating series. Converges by the alternating series test. But it's fine, you don't need to give an answer for that or for why, you just have to show your work there. And so we can finally say that the interval of convergence includes 1 but does not include negative 1, and so our answer is right there, and the work that supports that is all shown on the page here. Alright, so we'll go on to part C in the next video.